It's been a while, and welcome back. Today, I'm going to start writing some homebrew code to play music on this 1985 arcade board. If you've been following this channel, you'll know that I've spent 2 videos now talking about how I'm going to be writing this code, but today it's actually happening. By the end of this video, I will have this piece of hardware playing a note. Now you might be thinking, that's pretty unambitious, but let me reframe it in the context of the bigger picture. The goal for this series is to get Rob Hubbard's Commodore 64 arrangement of the Commando music to play on the original arcade hardware. And what these first 3 episodes are really about is eliminating the unknowns. When we started out, this thing was a big green mystery box. After the first video, we knew what it could do. After the second video, we knew how it worked, and by the end of this video, we'll know that we can control it. So, for that single note that I'm aiming for, if I can be in full control of its pitch, its timbre, and its timing, then what remains is just writing a sequencer for Rob Hubbard's music data, and that is not an unknown. In a previous project, I'd already converted Rob's player from 6502 assembler to JavaScript. For this one, I just need to rewrite it in Z80 assembler. How hard can it be? So, the first order of business will be to get something running on the target platform. Forget about sound for a moment. To start, I just need to be able to type some code and see evidence of it running. To do that, I'll need an assembler and I'll need a runtime environment. The runtime part is an easy call. Once I've got something worth listening to, then I can validate it on real hardware. But for the vast majority of development, I'll be using the MAME emulator and its built-in debugger that you saw last time. But the assembler, that's a tougher one. Over the 5 decades that the Z80 has been around, countless dev environments have come and gone, but to the extent that its surviving programmers have standardized on a toolchain, this is not it. Galaxiasm was a rabbit hole of mine from a couple of years ago when I was tinkering with Galaxian hardware and got so carried away writing scripts to build custom ROMs that they ended up becoming a standalone assembler. I would recommend this one to precisely no one, and I'll admit I'm choosing it out of familiarity rather than its merits. But at the end of the day, it'll do the job, and Z80 assembler is Z80 assembler. So I know I'm going to regret this one, but that's our toolchain. And this is my first attempt at writing a program for it, though I hesitate in good faith to really call it a program. All it's going to do is fill in the entirety of Commando's sound ROM with a single byte. 4000 is 16K in decimal, which is the size of Commando's sound ROM, and let's talk about this 3C. So this is a handy guide to the instruction set for the Z80. I'll introduce this now because I expect we'll be seeing it a little more in future. If I look at the single byte instructions, then the one with the code 3C is a really simple instruction that just increments the A register or accumulator. It does nothing fancy in itself, and that's kind of the point. I wanted something super simple that I could unambiguously see running on the target hardware. So this program won't do anything useful in itself, but think of it as a proof of concept for the development pipeline. I'm going to be assembling it using the real assembler and then debugging it using the main debugger. So if we can get this running, we have our tool set up for the rest of the project. So let's give it a try and let's assemble it. And let's take a little sneak peek. And there's our 3Cs. So to see this running, I'm going to copy the file that I've just generated over the top of the usual sound ROM that MAME uses for Commando. And let's run MAME, this time in debug mode. Okay, right away, we can see a good sign. MAME is complaining that the checksums for the sound ROM is not what it expected. So at least that gives us some confidence that it's actually running our code. Let's turn our attention to the debugger. By default, MAME's debugger is going to look at the main CPU for the game, which isn't the one we're targeting. We've been targeting the sound CPU, so let's give that one focus. And there is our sound ROM, a whole 16K worth of the repeated instruction Inc A, and there's our 3C on the right. So, big moment. I'm going to run our very first line of Homebrew code on this platform using the single step command. When I do that, have a look at this 0 value in red on the left. That's the value of the A register, and as I run this, we're expecting this to get bumped. Ta-da! I can do it again. And we have a working program. There is one little quirk though that I want to show you here. Watch what happens as I keep executing this when I go past instruction F. We think it's going to go to 1-0 now. It actually goes to 0. For some reason, the sound hardware has been reset, and I think I know what's going on here. In the first episode, we looked at the connections to the sound hardware and saw that there were 2 reset lines coming in. One of those is the master reset that's connected to pretty much everything else on the system, but the other one traces back to the main CPU where it seems to be memory mapped. In other words, I think that the first thing that the main game does on booting is to pull the reset line of the sound hardware down low. I don't know if it needs to do that. I don't think it's going to be too consequential. It means that the first few instructions of our sound code are going to be run twice. I don't think it's going to matter. Point is, we now have code running. We have a development pipeline. Let's play some sound. Quick programming note, in just a couple of weeks, I'll be speaking at the Vintage Computer Festival SoCal in Orange, California. Come see me demonstrate this project live and stop by at the booth to say hi. More details at vcfsocal.com. So, now that we know we can run code, it's time to play our first note. And to do that, I need to make a very big decision. Last time, we took a deep dive into how the arcade sound resources are used by the native music player and sound effects generator, and the conclusions from that have effectively dealt us a hand's worth of options for how to play music. Option 1 will be to play the music on the FM synths. Under this plan, I'll take over all 6 FM voices that the native music player would use, and keep the SSGs playing sound effects. That would let me mimic the SID using the most sophisticated tech that the OPNs have on board, and would mean that the sound effects engine would basically need no modification. It's such an obvious solution that you'd need a very good reason to consider anything else. So let me volunteer one. If you've heard much FM music, you'll notice it has a pretty characteristic sound to it, and that sound has a whole different personality from the Commodore 64's SID. Whether one is capable of modeling the other is an unknown right now, and the path to finding out looks like it cuts through some pretty gnarly math that I have no experience with. Can I find some FM parameters to create a square wave? Sure. Can I adjust those parameters in real time to adjust the pulse width? I don't know. So what's the alternative? Option 2 will be to play the music using SSG voices. Now, there's an obvious problem with this, which is that the sound effects generator uses all 6 of them. But I think I can take over 3 of them for music playback if I can squeeze all of the sound effects onto the remaining 3. That actually shouldn't be too hard. From the deep dive last time, I know exactly where in ROM these sound effects are assigned to chips and priorities, and diverting them would mean just changing 2 bytes per effect. There would of course be side effects. Some of the sound effects would interrupt each other or be masked instead of playing concurrently, but I'll just say it should be doable. However, if the FM core is a generation ahead of the SID, then the SSG is definitely a generation behind. It won't be able to play anything but square waves and a single channel of noise, and the volume envelopes would have to be done in software. But that simplicity is its virtue, and I should be able to quickly and easily get at least some music playing on it. And then there's some more creative options. A few of you commented after my first video that I could achieve this project's goals by using real hardware. For example, wiring a real SID into the Commando board, or using some of its I/O lines to remote control a Commodore 64. That would work. But there's one aim of this project that I don't want to compromise on, and that is that its end result should just be a ROM swap. That might mean that my music won't sound exactly like the C64, but it'll make it much easier to enjoy on a real arcade board or under emulation. And it should make for a more fun programming journey, which for me is kind of the point. That said, for the wildcard option, I actually had something else in mind. This is not a Commodore 64. It's its older brother and my very first computer, the VIC-20. Its sound hardware is even more basic than the SSG. And yet, in this incredible demo by Alexei Eben, here it is playing one of Rob Hubbard's most technically demanding pieces of SID music. If you're wondering how, the answer is software emulation of the SID. The CPU right now is running Rob's music player natively, but instead of controlling a real SID, it's controlling an emulated SID whose output is sound samples. Those samples are emitted by the real sound hardware by just wiggling its volume control, much like what you saw the C64 doing in the first video. I am in awe of this project. It is an amazing achievement, but I don't think it will be the right approach for me. If you listen to the Commando tune on it, you can tell it's pretty scratchy, and I don't think that's because of the limited precision of the volume wiggler. That thing is effectively a 4-bit linear PCM scale, and if I quantize the original Commando tune to 4-bit samples, then it's surprisingly good. So I think the scratchiness is less about the sample depth and more about the sample rate, and I doubt that's something I can do much about. In Alexei's README for the project, he talks about how the CPU is maxed out achieving a 6 kHz sample rate, and since Commando's sound CPU has roughly the same power as the VIC CPU, I'm not going to be able to do any better. And that level of scratchiness is not something I think I can live with. But there's a bigger issue, which is that if I'm maxing out the sound CPU with music playback, then I'd have no resources for sound effects, and that's kind of a deal breaker. So, time to play our hand, and after a lot of thinking, I have a conclusion. The sound tech that I'm going to use for this project will be the FM synths, but not yet. Getting the sound we want out of them is going to be hard, and if I try solving that problem at the same time as writing the music sequencer, then I would expect it to take longer than tackling them separately. So instead, I'm going to start by targeting SSG voices, which I hope I can use as an easy-to-use piece of scaffolding. I can use them to test the sequencer as I develop it, and then when I'm satisfied that that's working, I can replace just the back end with an FM solution and hopefully get it sounding better. One benefit of doing it this way is that it'll give me a little longer to do some FM research. And on that topic, I have some good news. In the first video of this series, I lamented the unavailability of documentation for the OPN sound chip, but since then, things have improved considerably. A number of folks in the comments pointed me to some adjacent documentation for Yamaha's comparable sound chips. One person pointed me to a sound programming book for an NEC computer that featured the OPN, and best of all, you might remember that I said the only known copy of the OPN applications manual was behind glass at a computer museum. Well, now we have it, thanks to one viewer in Coincidentally, my old neighborhood in Tokyo, who went out to that museum, spoke to the staff, photographed it, and uploaded the whole thing to the Internet Archive. And what's particularly astonishing about that is that this all happened within 3 days of me uploading the first episode, which was, yes, my very first YouTube video. And I want to take this opportunity to say a very big thank you to everyone for watching and showing your support. I don't think I've ever seen such kind, positive, and helpful comments to YouTube videos, and I want you to know that means a lot to me. Thank you. So, to play our first note on the SSG, I'm going to use the AY's original manual as my guide. It's old, but it's really comprehensive, and it's in English. Towards the back, there's a few demos of different sound effects you can make with it. The simplest is for a, quote, European siren, which looks like a good starting point. Now, it's not exactly sample code. Instead, it's telling me which registers to set to which values to get the effect. However, last time I mentioned that the way the OPN works was a bit weird, and setting registers is where that weirdness comes in. To explain what I mean by that, let me first show you what it means to set a register on a non-weird chip like the Commodore 64's SID. If you look at the machine's hardware reference manual, you'll see how each register is mapped to an address in memory. To update a register, just perform a single write to its address, and you're done. If you looked at what's happening in hardware during that write, here's what you'd see. First, the register number would be fed to some dedicated address pins, and the desired value for that register would be fed to some data pins. Once those are set up, a couple of control lines get tickled to tell the chip to initiate the write. But how are these values being supplied? Step back a layer and you'll see that the data lines are coming directly from the CPU's data bus, and the address lines are coming from the CPU's address bus. Now, that address bus is going to be much wider than the register space of the SID, so the upper bits are used to determine if it's actually the SID being addressed. Only if that's the case will the SID's chip select line get triggered. There's just one more thing to know about here, which is the read-write pin, which gets fed from the global broadcast signal. This pattern is very, very common. You'll see it for sound chips, graphics chips, memory, peripherals interfaces, you name it. Just not the AY, nor chips derived from it, including the SSG and the OPN. Let's start with the AY. Instead of dedicated data and address lines, it expects a single mixed-use bus and a set of control signals that reveal what's supposed to be on there. So, setting a register needs two interactions. First, you load the register number onto the bus and tell the chip to remember that number. Then you load the desired value onto the bus and tell the chip to assign that value to the previously chosen register. Technically, this would be a multiplexed bus. Less technically, it's kind of a clown car with values and addresses flopping out of it at some pretty inconvenient times. The reason it works this way is that GI designed this chip to interface with the quirky bus of their own CPUs, the CP1600 family, which were used in Mattel's 1979 Intellivision console and almost nothing else. And the clown car bus was, I suspect, a big part of the reason why not. It's manifestly a pain in the ass, and if you look at the design for the Intellivision, you get some idea of what coping with it looked like. To give you a taste, it uses one of the ROM chips for the operating system to address scratchpad memory and the sound chip. It relies on the ROM chip for the system font to address graphics memory, and the system RAM chip is the CPU's conduit to the GPU, as well as doing a whole lot else that has absolutely nothing to do with RAM. This whole design is kind of a clown class in computer architecture, and I really want to make a future video on just what a circus its components were. But for now, let's just say that the architecture did not catch on, and that the CP1600 family died with the Intellivision. However, GI had been marketing the AY to a wider audience, dubbing it the Jiminy Cricket. And while that name most certainly did not catch on, the chips themselves did, leaving the designers of computers, arcades, pinball, and consoles to figure out how to attach it to more conventional CPUs. To see how they did that, take a look at the sound hardware for Capcom's earlier title, 1942, which attached a couple of AYs to a Z80. For this one, the clown car control lines are driven by some glue logic, which is downstream from the Z80's address bus. The effect is that when you write to one address, it configures the AY to receive a register number. And when you write to the address immediately after, it configures it to receive a register value. Now you might be thinking, sure, but what does any of this have to do with Commando? And the answer is that when Yamaha released the OPN, they designed it such that you'd effectively set its registers the same way that 1942 did for its AYs. Unlike the AY, the OPN does have separate data and address lines, but the address line is only 1 bit wide, giving it just 2 locations. And déjà vu, you write to the first location to tell it which register you want to set, then write to the next one to assign that register a value. This seems absurdly indirect, but this chip was already maxing out a 40-pin package due to AY/SSG compatibility, and allowing direct register addressing would have needed an additional 7 pins. As a tangent, it's surprising that even for the Yamaha chips that didn't contain an SSG core, they still went with the same indirect addressing scheme. Maybe they just wanted a pin count as low as possible, but there's a part of me that wonders whether the architecture of Yamaha's whole FM platform, even into the 90s, was downstream of decisions that GI made back in the 70s. So this right here is my implementation of the European siren sample code, but I've taken one little liberty. The original code actually plays 2 notes with a delay in between. I guess European sirens famously went Ninor in 1979, but I don't have an accurate timer right now, and I really just need to hear a single note anyway, so forget the Nor, I'll make do with the Ni. In terms of code, it looks like quite a big file, but it's really just one simple pattern repeated over and over. That pattern is to load the accumulator with a register number, which I then store in the OPN's register number address. Then I load it with the desired value and write that to the OPN's register value address. There's quicker ways of doing that, but I just wanted something foolproof and straightforward to start with. So the manual tells me to write zeros to all the registers it doesn't explicitly mention. So those are at the top of the code. Then it gives me explicit values for registers 0, 1, 7, and 10, which I set at the bottom before ending up in an infinite loop. Perversely, the manual quotes the values for the registers in base 8. I cannot imagine why, so I've converted them into hex for this code, thanks to the macOS calculator inexplicably having an octal mode. So let's get it running. I've added a little makefile now, which will compile it and save me having to manually copy files around. And it's very underwhelming. It's very underwhelming. This is not working, and it's a bit of a puzzler because there's really not much that can go wrong here. When we look at what the code is trying to do, it all seems perfectly reasonable. First, we set the frequency value of the note. That needs a 12-bit value, so we have to first write the least significant byte, then separately the most significant nibble. The next thing we do is update the enable register to turn on the channel A square wave generator. Then finally, we set the volume of channel A to its maximum. So I had to play around and nothing's working. I tried a whole bunch of different frequency values, different channel volumes, nothing. The enable register is a little weird because it seems you have to set its bits to 0 to turn them on, not 1, but flipping them upside down doesn't make a difference. I even tried adding a delay between writes to the sound chip. Not that the manual says you have to, but it's been stubbornly silent this whole time. So I tried adding instrumentation to MAME so that I could watch all of the writes coming into the chip. And the good news is it's reporting the values I was expecting. So at least my code is doing what I think it's doing. The question then is, so why am I not hearing a peep? Fortunately, I have one last tool for debugging at my disposal. I know that at least Capcom's code can get sound out of this thing, so let's run the original code through that same instrumentation and see what they're doing that I'm not. The first thing that popped up was a couple of unexpected writes to registers 45 and 46, and what's particularly weird about these is that they are addressed by the CPU, but not then given a value. I found some documentation for these registers in the datasheet of the OPN, and apparently they're for a clock divider. I need to make sure that my own code configures the divider in the same way that Commando does, or my pitch is going to be wrong. But I wouldn't expect this in itself to make the difference between playing sound and not playing sound. No, of course not. So at this point, I added some strings to my instrumentation to see more clearly what the Commando code was doing, and I noticed something very strange. Consistently, I was seeing it write to the volume control for channel A, but not for channels B or C, and more puzzlingly, it was writing to registers 8 and 9, which according to the manual, do not exist. For some reason, the rows in the table go straight from register 7 to register 10, and after a lot of time, and I mean a lot, I finally realized why. This is not register 10. You might think it is, since that is a 1 and that is a 0, and a 1 followed by a 0 does spell 10. But only in decimal. For reasons I cannot even begin to imagine, GI were quoting the register numbers in octal, and then never mentioning that they were doing that. So the volume control for channel A was actually in register 8, with everything after it pushed forward accordingly. And if I adapt my instrumentation to not include the 2 register gap, then the results from Commando make a lot more sense. Seriously, by this point in my career, I've had decades of experience of misreading technical documentation, but that's a new one on me. I have no idea what kind of crazy smoke was blowing around the technical writing circles of 1979, but those must have been some wild parties, man. Getting back to it, updating my program meant just changing a single register number from a 10 to an 8. And lo and behold, honestly, I don't think I've ever been so mad about getting something working. Anywho, now that I had a note playing, I wanted to try messing with its parameters to make sure that my understanding of the AY controls matched reality. First off, the enable register. Sure enough, I can silence voices by writing all ones to it. I can bring back the original note by lowering only the bit for channel A's tone generator. Or make it play noise by instead lowering only that channel's noise bit. Now that I've got it playing noise, I can use the global noise period control to change its pitch, going from this at one extreme to this at the other. Right now, channel A is at full volume, and if I want to lower that, I can use the channel A amplitude register. The fall off, I'd note, is pretty steep, with most of the lower levels being comparatively inaudible. At this point, I'm going to say that we've got the timbre of the note under control, though it's a little tenuous. The AY isn't capable of much variation in timbre, but to the extent that it is, I think we've established control over it. So I'm going to mark that goal as achieved for now. There'll be a whole lot more to do when we move this to FM. So next up is pitch. To see this one in action, I'm going to set the least significant 8 bits, what the manual calls fine-tuning, to 0, and show you what happens as I increment the most significant 4 bits, which the manual calls course timing. Surprisingly, as the numbers go up, the pitch of the note actually goes down. That's because what we're specifying here is actually the note's period or wavelength, not its frequency. To demonstrate that, if I start at a pitch value of 100 and keep doubling it, you can hear that the note falls 1 octave at each step. So at this point, I can say that we understand how the AY's pitch works, and while we definitely do have agency over it, I can't say that we're fully in control. The difference is that I need to be able to make it play an exact note of my choosing. I need to be able to specify a frequency and hear that from the AY, and to do that, I need to do some calibration. Since the frequency of the note is inversely proportional to the pitch value we're giving it, there must exist some constant, which, if I divide by the pitch value, will tell me the frequency I'll get out. So I need to know what that constant is. The way I'm going to find this out is just to earball it. That's like eyeballing something, just using your ears. I'm going to play a note on the SSG with a known pitch value, and then try measuring the frequency of the sound that comes out. Once I've figured out what the frequency is, I can derive the constant. For this little experiment, I chose a pitch value of 64, and after a little while, I concluded that the frequency I was hearing was 1465 Hz. This meant that my magic number was 93,760. But there's a little more to this. What I really want to do is not have the AY play a chosen frequency. I want it to play the frequency that corresponds to a chosen pitch value for the Commodore 64's SID, and that's going to take a little more math. Unlike the AY, the SID's pitch values correspond to frequencies, not wavelengths. So its formula for frequency has a constant that gets multiplied by a pitch value, not divided by one. And thanks to some other people having done the work already, I don't need to measure this one. The magic number for a PAL Commodore 64 SID is 0.05872536 Hz per pitch unit. I should add that that number will be slightly different if this were an NTSC Commodore 64, but since the Commando tune was originally written for a PAL one, that's the number that we're going with. So if I go back to the AY's tone generator and substitute its frequency parameter for the equation that predicts the SID's frequency output, then a little bit of rearrangement will give an equation that relates an AY pitch value to a SID one. The value that I need to feed the AY is 1596312 blah 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 divided by the SID value. Let's put that to the test. I'm going to pick an arbitrary value on the musical scale and see if I can make the AY play that note given only the SID value for it. The note that I'm going to play is the A above middle C, otherwise known as A4, which by definition is 440 Hz. To translate that to a pitch value for a PAL SID, I'm going to use a German copy of the Commodore 64's user manual, and it's telling me I want a value of 7,493. So, if we divide our enormous constant by 7,493, that would predict an AY pitch value of 213. So, let's modify our assembly program to play its note using that pitch value. And, well, here's the note we were hoping for, and here's the note we get. Victory at long, long last. But we're not there yet. Right now, we need a, let's call it, compile time calculator to convert the pitch values, and that's a problem. Many of the effects in Rob Hubbard's music routine, like vibrato and drums, dynamically update the pitch, so we'll need to perform the division at runtime. And that's not the easiest thing. The Z80, like many of its 8-bit contemporaries, had a pretty limited ability to do math. It can add, it can subtract, it can perform logic operations and do bit shifts, but if you wanted a multiply or a divide, then, well, those are your building blocks. Fortunately, it's possible to achieve a divide using just comparisons, subtractions, and bit shifting, using what is effectively the binary equivalent of the long division algorithm taught to kids. It's just going to run very slowly and be an absolute chore to write. Fortunately, one of the upsides of coding for a CPU that turns 50 years old this year is that there is an abundance of solutions to common problems that coders are going to face. So I should be able to just jack into cyberspace and download some other coder's long division algorithm. That actually proved harder than I was expecting. What I needed was code that could divide a number at least the size of our giant constant by the size of a SID pitch value, and eventually I came across a 32 by 16 divider that looked like it was going to work. But it didn't. Sadly, this code was relying on CPU instructions that don't exist. Well, kinda. If you look closely at the numeric codes for the Z80's instructions, you'll find that there's gaps in there, leaving people to wonder what was in them. For many of these values, trying to execute them would result in unhelpful random behavior, but many of them proved deterministic, and some of them even did something plausibly useful. I've most often heard these described as undocumented instructions, though I've always hated the term. I was first introduced to these on the 6502 as quasi-opcodes, which captures much more faithfully what's going on here. These are not instructions that were designed but left unchronicled. Instead, what we're seeing here are the unintended side effects of the design that implemented the other instructions. And for that reason, I'd rather not use them. Now, Zilog called last orders on the Z80 surprisingly recently, and by now I expect that everyone that's ever going to be made has already rolled off the production line. But still, I am, when not tinkering with retro hardware, a professional software developer, and knowingly relying on unintended side effects is something I'd rather avoid if I can. And fortunately, I can. Rolling back the commit history of this file, I was able to find an earlier version that used only organic, honest-to-goodness, all-natural Z80 instructions. So I put it to the test. I hacked together a little program that just loads parameters from RAM, performs the divide, and stores the results back into RAM in an infinite loop. So using MAME's debugger, I could plug values in and watch the results come back in real time. This is it, by the way, doing the same calculation of the 440Hz A4 that we did by hand a moment ago. The result is 1 unit different. I'll take it. All that remained now was to hook it into the tone generator, and in very little time, I had a little demo that let me feed SID pitch values into RAM and listen to them as I typed. We are getting close to the end now. I still got 99 problems, but pitch ain't one. Last job today is to specify the timing for the note. Clearly, the sound hardware already has some kind of timing source hidden away somewhere. I just need to find it. Looking at the schematics, there's only one device belonging to the sound hardware that has an inbuilt timer, and that's the OPN sound chips. Unlike the AY/SSG, each of the OPNs apparently has 2 timers at its disposal. But that can't be it. Last time we saw that the chips are hardwired to be write-only. And the IRQ pin that the timers could have used to signal a timeout isn't even wired up. So it has to be something external, meaning either the 3 MHz master clock signal or the external interrupt line. And I can say right now, it has to be the interrupt line. If it was just the master clock signal, then Capcom would have had to have written time-critical, cycle-counted code, which would be a ton of effort, and I've seen their sound code. They didn't do that. So if I trace the interrupt line back to its source, then we see it's coming from some custom logic chip. So all bets are off as to exactly how it behaves. But I do notice that it's downstream from the video timing signals that determine the current scan line. So clearly this thing is timing related. It's just going to be up to me to measure it to find out what the period is. So here's what I'm thinking. This is a super simple program that will just count interrupts coming in. The idea being that if I know an interrupt count and a period of time that that count was accumulated in, then I can just divide one by the other to learn the interrupt rate. Let me talk you through it. It's pretty simple. Right at the start, I set the interrupt mode to the same one that the Commando sound code would do. Then I just get stuck in an infinite loop. When the interrupt comes in, the Z80 is going to jump to the address 38. It's hard-coded in the chip, where I will run my little interrupt handler that just increments the count. Let me show you it in action. Okay, let's get all of that out the way. Let's look at the audio CPU. And okay, we remember from earlier that the first thing that's going to happen on boot is that the main CPU is going to reset the sound CPU for some time. We don't know how long that is, so right now it's in an infinite loop, and at some point it's going to go back to 0. There we are. So it would seem that the main CPU has stunned the sound CPU for 5 frames while it boots. That's fine. That's just going to be our 0 point for the timing. Let's bring up a RAM viewer. RAM starts at 4000. So right now our count is 0. Let's start it running, and you'll see in that first byte of RAM, each time we have an interrupt, that number is going to increment. When it blows past FF, it's going to bump the next byte. If that bumps past FF, it's going to bump the next one, and so on, potentially forever. So you can see it counting up happily here. I want to get a good number of interrupts in a sample before I divide it. So I'm going to set a watch point to trigger when the third byte of the count gets bumped. That's going to mean we've got like 64K interrupts. Sounds like a good sample for me. So watch point set at memory location 4002 for a 1 byte, if that's a write, and the watch point data is 1. That's going to take a long time, so I'm going to F10 this, put it into warp mode, and just sit and wait. Okay, here we go. So we are now at frame 16290. So let's bring up the calculator, and just to show you what we're doing, we had 10000 interrupts so far, which is 65536 in decimal, and that is going to be divided by what, 16290 minus the 5 frames that we started from is 4.02 interrupts per video frame. It's a little surprising. I would have expected it to be a whole number. Given that the custom logic chip is feeding directly from the scanline counter, I would have probably expected it to be frame aligned, but seems like it isn't. Let's try something. Let's boot MAME again, but not in debug mode. Okay, frame rate for the game is 59.637405 hertz. So will you look at that? As far as I'm concerned, that is exactly 240 interrupts a second, just with a rounding error. Couple of thoughts on that. First, it's reassuringly high. I wanted it to be at least 50 so that it wouldn't be fewer than the interrupt count of the Commodore 64 Commando. We've cleared that hurdle. We might have the opposite problem, which is if the interrupts are too frequent, then each one is going to be pretty short. So I'm going to make sure that in the worst case scenario, I've still got all of the work done within one of these short time frames that I need to. But okay, we know that number is 240. Let's see if we can put it to some use. Okay, a new program, a little more complicated, but not much. This time my interrupt handler is doing a count down instead of a count up. I've also put some code in here to play a note. Let me show you that running in itself. We have a note. Okay, I'm going to make a little change, bringing in a silencer. So right at the start, we set the accumulator to 240, which is what we think is the number of interrupts per second. In the interrupt code, where is it? I decrement the accumulator, and if that's 0, I silence it. So if my experimentation is correct, this should play a note for exactly 240 interrupts, meaning exactly 1 second. Let's give it a try. I can believe it. Yeah, okay, let's be a little more scientific about this. I'm going to run MAME again, but I'm going to siphon off the audio output to a file that we can then analyze. So, okay. And let's bring that into Audition. Is it there? Okay, let's chop off all the silence at the start. Where does that start? It's good to me. And that looks very happily around the 1 second mark. Let's zoom in. Oh, that is perfect. So that's the last of our goals met for our proof of concept. But I said at the start that I'd be playing this note on the arcade board. So it's time to take this code out of MAME and onto real hardware. This turned out to be a moment of truth in more ways than one. Before I could see if my code worked, I needed to check that my board still worked. Because, to be perfectly candid, I've been using it as a prop all this time, but the last time I actually powered it up was 14 years ago. Fortunately, it turned out to be fine. So let's say a fond farewell to its sound ROM and thank it for its service. Before I try running my own code on this, I wanted to check that the game plays okay without the chip. Theoretically, there are no dependencies on the sound system, so the game should still play fine, just with no audio. But let's just check that first. All is good. So to get my own code running on this thing, I have a few options. The original chip is actually reprogrammable if I were to peel off the little label and shine UV light through the window underneath, but it's a piece of history, and I think it deserves a more dignified retirement than that. I do have spare chips just like it, but that's the hard way. The easy way will be to use an EPROM emulator like this one. It's essentially just RAM with two interfaces. One is a USB port, allowing me to remotely program it. The other is a probe that plugs into an EPROM socket, so it can pretend to be a real chip. This particular one is the My Geeky Hobby one. I'll put a link in the description for more details. So first let's check that the EPROM emulator itself is working okay. I'm going to upload Commando's original sound ROM to it, so I'd expect the game to be fully back to normal. Okay, our tools are set up. Let's try uploading our proof of concept note player. And So that's our note, but it's a bit blink and you miss it. So I've made a couple of changes to the code. One is that the interrupt handler will now fade the volume down of a note after you play it. The other thing is I'm polling the sound latch. So when you put in a new sound code, it will play a note. Just for funsies, I've had it use that sound code to look up a pitch value from an entry of SID pitch values. I then take that through the divider and put it to the AY. So it's not fancy, but it's a start. What it needs now, of course, is a sequencer, and that will be the goal for episode 4. I thank you. So, after the next seemingly interminable wait, join me for a deep dive into how Rob Hubbard's classic music player works, and we'll be hearing the first implementation of a whole song on the Capcom Commando platform. Until then, thank you for watching, and please, do continue.